Hi, I wanted to talk a little bit more about why getting an outcome in the tails, the t-curve, allows you to reject the null hypothesis. The data set, or the combination of participants that you end up selecting, is one possible combination of participants that might be selected, and it has a t-score that's calculated based on the data values in that combination. And it's also a member of a set of possible samples that might be selected in your study. And the t-scores of all of those possible samples fit under this t-curve, this t-distribution. They fit under this curve when the assumptions of the study are met. That's why it's important for the assumptions to be met, is because if the assumptions are met, then the correct type of curve goes around the t-scores of the possible samples. And if you've collected data from 17 people, then the t-scores of all of these possible samples of 17 people will have a curve around them, and that curve will be a t-distribution with 16 degrees of freedom. And if you select a combination of people that gives you a t-score beyond the critical value, that's when you can reject the null hypothesis. So maybe if this is the rejection region, and you get a sample of 17 with a t-score above this critical value right here, you can reject the null hypothesis. And I talked about how all of the possible combinations of 17 people that might be event selected will have its own t-score. Some will have higher t-scores than others. And there's a curve that outlines the possible the t-scores of the possible samples. But this distribution, or this stack of possible samples that I'm creating under this curve, is actually the set of possible samples that would be found in a situation when the null is true. So what this curve is, this curve that says t-distribution with 16 degrees of freedom actually is it's actually the curve that outlines the possible samples that would be found in any type of research situation with that has 16 degrees of freedom and the null hypothesis is true. So anytime you're doing a one sample t-test with 17 people and your degrees of freedom, the degrees of freedom of your data set is 16, the curve that outlines the possible samples in a situation when the null is true is always this type of shape. So it's really a hypothetical set of possible samples that would exist in the situation when your null hypothesis is true. In the situation when the null is true, most of the samples have t-scores. Well, not most of the samples. The highest stack of samples is at the t-score of 0. And the samples that give you a t-score of 0 are all of the samples that show no evidence that the null hypothesis is wrong. Because a larger test statistic shows more evidence that the null is wrong, and a test statistic of 0 shows no evidence that the null is wrong. And in a situation when the null is true, it makes sense that you would have the largest stack of samples at 0, because when the null hypothesis is true, any evidence that's found against the null hypothesis in a data set is just happening by chance. So there should be a lot of possible samples that give you no evidence that the null is wrong. And it should also be more and more difficult, or I mean, the samples that give you higher test statistics with more evidence that the null is wrong should be more rare and harder to find. There should be less possible samples that give you this large test statistic in a situation when the null is true. Because if the null is true, there aren't very many data sets that will contain that much evidence that the null is wrong. So these data sets out here, further from 0, are showing more evidence that the null is wrong. And they're also the types of data sets that are more unlikely to appear in a situation when the null is true. These data sets, or these combinations, further from 0 to the left end, are also showing more evidence that the null is wrong. And they're also more rare, or harder to find in a situation when the null is true. So this curve is really a hypothetical curve, or a hypothetical distribution of samples that shows how many samples would have each of these t-scores in a situation when the null is true. And it turns out in a situation when the null is true, a lot of samples will give you 0, and fewer samples will give you t-scores further from 0 toward the tails. So you have this outcome out here has a high t-score, a really high t-score, which means, well, maybe not really high, but high enough. And since this outcome out here has a high t-score far from 0, it's also an outcome that gives high evidence that the null is wrong. And it's a very rare combination in this situation when the null is true, because it's really rare. The combinations that show a lot of evidence that the null is wrong are rare in this situation when the null is true. Not very many combinations will give you this kind of evidence against the null hypothesis if the null is really true. So basically here, what you've selected is an outcome with a large t-score with a lot of evidence that the null is wrong, and it's also an outcome that's unlikely to be found in this hypothetical situation when the null really is true. And if it's unlikely, if this combination is so unlikely to be found when the null is true, it's also an outcome that lets you reject the truth of the null hypothesis. And that makes sense, because if there's a very small chance of finding this combination, if there's a very small chance of ending up with this combination in your data set in a situation when the null is true, you can reject the truth of the null hypothesis, because whenever something happens that's unlikely to happen in a certain type of situation, it lets you question the situation itself. And what do I mean by that? I think I was talking about if you cough 10 times in the same day, that's unlikely to happen when you're not sick. It's unlikely to happen in the situation when you're not sick. So if you do cough 10 times, that outcome lets you question or maybe even reject the idea that you're not sick. And the logic is the same in a hypothesis test. You could actually look at if you have a curve that shows how many coughs you've how many times you've coughed in a certain day. These 0 is showing no evidence that the null is wrong. Well, first I have to say what the null would be. Remember that the null is always the absence of something. And in this case, it's the absence of a cold. So coughing 0 times is an outcome that shows no evidence that the null is wrong. It's giving you no evidence to believe that you're sick. It's giving you no evidence to reject the idea that you're not sick, it gives you no evidence to reject the idea that you're healthy. And this outcome of 0 coughs is also likely to happen when the null is true. If you're not sick, you're likely to cough 0 times, because why would you cough if you're not sick? So 0 is likely to happen when the null is true. Just like how you're likely to get a t-score of 0 when the null of your study is true. Once you get further from 0, you're getting more evidence that the null is wrong or false, because the more times you cough in the same day, the more evidence you have that that this statement of you not being sick is actually false. So you're getting more evidence that the null is false. As you move to these higher numbers. And if you cough 6 times in the same day, this is actually probably a point where it's an event that's pretty unlikely to happen, or it's pretty rare in a situation when the null is true, or in a situation where you're not sick. And since it's unlikely to happen in this hypothetical situation where you're not sick, it's an event that lets you reject this null hypothesis. So coughing 6 times is rare if you're not sick, if the null is true, just like how getting this large t-score in the rejection region is rare or unlikely in the situation where the null hypothesis of your study is true. And at a certain point in this number line, you could imagine there being a critical value, which is the point where the null will be rejected. And you could say, if I cough 5 times in the same day, this is the point where I consider myself to be sick. This is the point where I am willing to reject the possibility that I'm not sick. And if I cough 5 or more times in the same day, I'm going to reject this null hypothesis, because coughing 5 or more times is too unlikely. It's such an unlikely thing to happen when the null is true that I'm going to reject the null hypothesis. If you set your critical value at 5, then this whole area of the number line at 5 or higher is your rejection region. Meaning if you have an outcome that's 5 or higher, you will reject the null hypothesis. But if you get an outcome that's not in the rejection region, such as coughing 3 times in a day, that's not enough evidence to reject the idea that you're not sick, because it's something that could too easily happen by chance. It could easily happen by chance, even if you really aren't sick. If I'm not sick, I could probably cough 3 times easily by chance, just if I run into some dust. So that's the same logic. So I hope that analogy helps explain this concept of how you have a hypothetical situation that shows how you have a hypothetical situation when the null is true, and you have a curve that shows how likely each t-score is to be found in that situation when the null is true, and 0 at the center is showing no evidence that the null is wrong. And if you get an outcome far in the tails, far from 0, you have an outcome that's unlikely to happen in that hypothetical situation where the null is true, and it lets you reject the null hypothesis. If you have any questions about this, feel free to ask me. In this video, I just wanted to give you some more of the intuition of why an outcome in the tails would let you reject the null hypothesis.